Hello everyone, thank you for watching this video. In this video, I'm going to talk about our work on file updates under random arbitrary insertions and deletions. In cloud backup system like Dropbox, the client may upload an edited version of his or her file to the Dropbox server, and the Dropbox server may transmit something to update the client's other devices. We are interested in minimizing the transmission cost of this situation. This is our communication model. The old file X is available to both encoder and decoder. The new file Y is obtained from X through some insertion-deletion process and is available to encoder. The encoder takes X and Y as inputs and encode to a transmission and send to the decoder. The decoder receives the transmission and combined with the old file, it reconstructs the new file, Y prime. We modeled two different insertion-deletion processes. The first one is a random pre-edit source sequence left to right random indel process. In this model, the source sequence, the pre-edit source sequence, is uniform random IID from the source alphabet. The insertion-deletion process is modeled by a three-state Markov chain, and the transition probabilities of this Markov chain is set to be as shown in this figure. Hence, the insertion-deletion process is an IID insertion-deletion process. Here, we are going to show an example how a pre-edit source sequence undergoes the insertion-deletion process to obtain a new sequence. So eta here means no operation. Hence, the symbol is remained in the new sequence. Iota means insertion, and it inserts a symbol uniform drawn from the alphabet. Delta indicates an deletion. So in this way, we obtained a new sequence which we name post-edit source sequence. The second model of the indel process is arbitrary pre-edit source sequence, arbitrary indel process. In this model, the pre-edit source sequence is an arbitrary length and sequence from the alphabet, and the indel process is insertion and deletion occurred to arbitrary positions, inserting arbitrary symbols from the alphabet. The only constraint is that there are at most epsilon n insertions and delta n deletions. For these two different indel process models, we have different metrics for the communication model. In the random model, we want to get average communication complexity, and we allow small error decodability. Because in the random model, there may be atypical sequences and atypical edit process, which means there are a lot of insertions and deletions, but with small probability. For the arbitrary model, we aim on the worst case communication complexity, and we allow zero error decodability. Our contributions are in the following. We came up with information theoretic alphabet-sized lower bounds for both models. We came up with, we propose computational efficient achievability scheme, which is unified for both models. Our inner and outer bounds nearly match by a constant factor, and when the alphabet size is large, the inner-outer bounds match up to second-order term. This table is a summary of some recent prior work on file synchronization problems. So in the first column, the problem description. In the first four prior works, they modeled the problem as a two-way communication problem, while each for encoder and decoder, each one has access to one version of the file. In the sixth work and our work, we modeled the problem as a one-way communication problem. And in our problem, the encoder has access to both files. The decoder has access to the out file as the decoder side information. For the alphabet size, we deal with arbitrary alphabet size. The number of edits we deal with is a small but constant fraction of n, where n is the block length. A main contribution of our work is we derived explicit information theoretic lower bound for both models. A related problem to our work is the insertion-deletion channel. The similarity lies in the model, while our India process model is similar as the channel model when the channel error is synchronization error like insertions and deletions. The difference is that we minimize the communication cost, which is the entropy of the new file given the old file, and the distribution of the old file X is already given. In the insertion-deletion channel, the aim is to maximize the channel capacity over all the distributions for X. So from this perspective, the insertion deletion channel is a harder problem than ours. But the insertion deletion channel remained an open problem for a long time, and there are a lot of prior work came up with outer bounds and inner bounds for different channels, like only deletion channels, duplication channels, sticky insertion channels, and so on. Another related work is file synchronization problem. We have shown some prior work in the previous table. The difference from our work to the file synchronization problem is, firstly, in the file synchronization problem, each party only has one version of the file, while in our problem, the encoder has both versions of the file. In the second difference is that file synchronization, the most common model is two-way communication model, while in our work it's one-way communication. Here are the main results of our work. So for the random model, we came up with information theoretic lower bound, which is shown in theorem 3 in our paper. We've shown the achievable rate of our algorithm in theorem 7. We can see that the higher order term of the lower bound and the achievable rate differs by some constant times epsilon plus delta, where epsilon and delta can be interpreted as the probability of insertion and deletion. This constant decays very fast with the alphabet size. For the arbitrary model, we show an information theoretic lower bound in theorem 4. This lower bound is depends on the alphabet size. And if the alphabet size is large, we represent it as by Taylor expansion as this high order term plus a second order term, where the alphabet size goes to the second order term. This is presented in corollary 5. The achievable rate of our algorithm for the arbitrary model is presented in theorem 6. Comparing the corollary and the theorem, we can see the higher order term match up to a constant times epsilon, where the constant is 1. So now we're going to show the detail, a little detail about our work. So this part is about the lower bound for the random model. This is the most technical challenging part. We built on Canaria and Montanari's previous work on deletion channel with small deletion probability. The differences with their work is, firstly, our problem is a file update problem instead of a deletion channel problem. Secondly, because we mix deletions and insertions, this add to the complexity of this work. So the main idea of this part is we so the main idea is that we only care about some typical edit pattern where there are not too many edits. To be more explicit, we look at the extended run of every run, where the extended run is a run together with its two neighbors. And we say the typicalized edit pattern has no more than one edit in the extended run. So the pre-edit source sequence and the edit pattern will give the new the post-edit source sequence. And now we perturb this edit pattern to typicalized edit pattern based on the runs of X. So this typicalized edit pattern E hat is actually a function of X and E. And with this typicalized edit pattern, the typicalized post-edit source sequence can be obtained by processing E hat on X. This figure shows an example of all the sequences we've defined. So in the first line shows the pre-edit source sequence X. The second line is a more visualized way to show the actual edit. And the third line is the edit pattern described by the edits we defined before. So just to remind this, eta means no operation, iota sub 1 means an insertion of a symbol 1, delta means deletion. Y is the post-edit source sequence obtained by processing E on X. The next line, this E complement, is to indicate the edit we eliminated to get the typicalized edit pattern. So in this example, in the first run of X 000, the extended run is 0001, including the right neighbor. In this extended run, there is only one edit, so we don't eliminate any edit. Hence, the E complement is all no operations in this extended run. In the second run of X, which is 1, 1, 1, 1, the extended run is 0, 1, 1, 1, 1, 2. In this extended run, there are 4 edits, so we eliminate all the edits in this run. By default, we don't eliminate the edit to the neighbors when we look at this run. So we eliminate this deletion of the 1, this insertion of a 4, and this deletion of a 1. In the next run 2, 2, the extended run is 1, 2, 2, 3. Again, in this extended run, there is only one edit, which is this deletion of 2. Hence, we don't eliminate anything. And in E complement, it's all no operations in this extended run. In the next run 3, the extended run is 2, 3, 2. There are no edits in this extended run. Hence, in E complement, it's all no operations here. In the next run too, similarly, there are no edits in the extended run 3, 2, 3. Hence, a complement has all no operations correspond to this extended run. In the last run of X, 3, 3, the extended run is 2, 3, 3, and there is only one edit, which is this insertion of 3. Hence, in this extended run, we don't eliminate anything. So the only run we eliminate the edits is the second run of X, and it's represented in E complement by this delta underline out of 4 underline delta underline, where underline means eliminated. From E complement and E, we can get the typicalized edit pattern E hat just by eliminating the edits indicated in E complement. And from E hat and X, by processing E hat on X, we can get Y hat, which is the typicalized post-edit sequence. Here is the proof sketch for the lower bound of the random model. So as we described in the previous slide, we firstly perturb the edit pattern to a typicalized edit pattern, and we obtain the typicalized post-edit sequence from X and E hat. It can be shown that X and Y hat can be almost aligned. Hence, we can calculate H of E hat given X and Y hat, which we will call the typicalized nature's secret in the following. And we can show that this typicalized nature secret is close to the nature secret, which is H of E given X, Y. This term is the information that the encoder will never find out, even it has both X and Y. Or the other way to interpret is that even if the encoder has the edit history, by sending the edit history, he sent the redundant information, which will equal to this term, this nature secret term. The entropy of the edit pattern can be calculated, and the H of Y given X, which is what we want to minimize, can be written as H of E minus H of E given X and Y. This is because E is independent of X, and Y is a function of E and X. Now we are going to show how X and Y hat, sorry, it's a typo here. It should be Y hat, the typicalized edit pattern. How X and Y hat can be aligned by some length case analysis. So for a length L run in Y hat, and the next run to align in X is length L1, we'll have the following cases. And in those cases, we'll give an example where the length L Y hat run is 0, 0, 0, 0, 0. So the first case is that the parent run of this y-hat run is a single run in X. And there are three subcases in this case 1. So case 1.1 is that there is no edit in the parent run. Then the length of the parent run L1 equals to L. And the example is that it's a length 5, 0 run undergoes no edit and obtained a length 5, 0 run. Case 1.2 is single insertion in the parent run. Hence, L1 will equal L minus 1. And in this example, a length 4, 0 run with an insertion of another 0 obtained a length 5, 0 run. In case 1.3 is single deletion. In this case, L1 equals L plus 1. And the corresponding example is that the parent run is a length 6, 0 run. By one deletion, obtain the length 5, 0 run. So these three subcases correspond to case 1, where a single run in X leads to a single run in Y-hat. The second case, case 2, is that the parent run for this Y-hat run is a sub-run in X. In this case, L1 is greater than L. This is because an insertion of a different symbol in the X run, which break the X run into two runs. The corresponding example is the X run is length 7, 0 run, and by inserting a 1 after the fifth 0, it breaks the X run into two Y runs. So the first Y run is length 5, 0 run, and the insertion creates a length 1 run, which is a single one, and then this length 2, 0 run is also aligned to the parent run, the length 7, 0 run. In case 3, the parent runs are a lot of parent runs where the number of parent runs would be an odd number. So for example, 2t plus 1 parent runs. In this case, there are t plus 1 runs with the same symbol as the y-hat run. And they are separated by another t length 1 runs of different symbols. And the added pattern is the deletions of those length 1 runs, which will combine those t plus 1 runs of the same symbol into a single run in y-hat. In this case, L1 is smaller than L. An example is like this. So the t equals 2 here. So there are 3 runs of the same symbol as in y-hat, in the y-hat run, which are 0, 0, 0, 0, and 0. They are separated by t runs to t length 1 runs of different symbols. In this case, here there's a length 1 run of symbol 1. Here is a length 1 run of symbol 2. And by deleting this 1 and this 2, we obtain the length 50 run. So, this in these 5 cases, the lengths of the X run to be matched are almost different, except 2 cases, where in case 1.2, L1 equals L minus 1. In case 3, L1 can also equal L minus 1. In case 2, it's a single insertion. In case 3, when L1 equals L minus 1, and it will lead to length Ly hat run, is the case where the first parent run is length L minus 1 run of the same symbol as the Y hat run, and then a single symbol or a length 1 run of a different symbol, and then again a length 1 run of the same symbol as in Y hat run. Then by deleting the different symbol, the run get lengthened by length 1, results in a length Ly run. So in case 3, it would be a single deletion. So we would be able to show that the case 1.2 and case 3 can be further distinguished by tracking further symbols in X and Y hat, because they shift by 2 positions, and we will be able to show by further tracking no more than 4 symbols in both runs, the probability that one was still not able to distinguish these 2 cases can be upper bounded by order 1 over A squared. Similarly, case 1.3 and case 2 can also be ambiguous, and by similar method, we can show by tracking no more than 4 symbols in both sequences, the probability one still not able to distinguish case 1.3 and case 2 can also be upper bounded by 1 over A squared, where A is the alphabet size. So this is a flow chart showing the way to align X and Y hat. Sorry, again, this is a typo here. It's a long flow chart. I will decompose it and represent it in a better way before the submission. So basically the process starts by reading X and Y hat, breaking them into runs, and start from left, track each pair of runs to be matched in X and Y hat. So firstly, check whether they are composed of the same symbol. If they are composed of different symbol, we set the length of the parent run to 0. That is, we match the Y run to an empty run, and set the length set L to be the length of the Y hat run. If they are composed of the same symbol, then L1 is just the length of the X run. The L is just the length of the Y hat run. And then we firstly compare whether the L1 equals L. If L1 equals L, then we can tell it's case 1.1. There is no edit, and we can align this Y run to X run. If L1 is greater than L, we further check whether L1 equals L plus 1. If it's not the case, then we know it's case 2. And we can align the Y run and the next Y run to this X run because it's a single insertion of different symbol in the X run, which break it to 2 Y runs. And similarly, we can check if L1 is smaller than L, we can check whether L1 equals L minus 1 and so on. There would be some ambiguous local alignments event, which means by checking 4 more symbols, we can still not distinguish between case 1.2 and 3, or case 1.3 and case 2. In this case, we continue 2 different alignment for this local ambiguous alignment until we figure out one alignment is impossible. In some cases, both alignments are possible, which will give 2 different global alignments. In this case, we write 1 bit to a variable, which is the alignment, which we define by global alignment to indicate which global alignment it is. To show the local global alignment, we here give an example. So here, this is the Y hat sequence. This is the X sequence. We don't know how they are aligned. They are in general with different lengths. So firstly, we check the first pair of rungs in Y hat and X. The length of this Y hat run is 2. The length of X run is 3. So it may be 2 different cases. The first case is a deletion in the X run, reduce the length of the run by 1. The second possibility is there is an insertion after the second 0, which an insertion of a different symbol after the second 0. So the run is break into 2 runs. Then we check one more symbol after this Y run, which is 1. So if the second case is possible, the insertion must be a 1. So we keep both alignments now. And then we check the second run. The second run of Y hat is a 1, and in X is 4 ones. It's 1, 1, 1, 1. So in the first alignment, because the length now L1 is 4, L is 1, so it must be the case that there is an insertion of different symbol, break the 4 ones into 2 runs. And we check a symbol further in Y hat. This insertion must be a 0. So here we can match up to this 0, 0, 0, 1, 0, match with Y hat. And because this insertion of 0 is in this length 4 one run, it break it into a length 1 one run and a length 3 one run. However, after this 0 in Y hat, there are 4 ones. Well, because these 4 ones in X are in the round, and there's an insertion of 0 here, by the definition of the typicalized edit pattern, there will be no other edit in the extended round of these 4 ones. So there can be no other insertion of ones here, which means after this 0, the number of ones would be 3. However, the number of ones after this 0 in y hat is 4. Hence, we know the first alignment is impossible. So we don't need to continue align this alignment. In the second alignment, so this insertion of 1 break the 3 zeros into 2 rounds. So up to now is 0, 0, 1, 0. It matches with y hat. And then the next round to be matched in y hat is this 4 zeros. And in x is also 4 ones. In x is also 4 ones. So L1 equals L. It's the case 1.1. There's no edit in this one, so we can align them. And furthermore, the next one to be matched in y is this 2, in x is this 2, 2. So L1 equals L plus 1. Again, there is a local ambiguous alignment. It might be a deletion of a 2. Reduce this 2, 2 into a single 2. It may also be an insertion in between. Break this 2, 2 into 2 rounds. And by checking the next symbol in y hat, if an insertion happens, it must be an insertion of 3 here. So now there is an ambiguous local alignment. We start 2 different ways to align here. In the first alignment here, so there is a deletion of 2 here. This 2 to align to the y round 2. The next round to match is 3. In y hat is a length 1 round, and in x is also length 1 round 3. So L1 equals L. The length 1 round 3 is matched to the length 1 round 3 in x. And similarly, the 2 is also matched to this 2 in x. They are both length 1 rounds. And then the next round to match is the last round to match in y hat is the length 3 round 3. In x it's length 2 round 3. So L1 equals L plus 1. But because this is the end of sequence, we would know it is an insertion. It can't be a deletion length and round because there are no further symbols in x. So in this line, this global alignment 1, this alignment can lead x to y hat, and the edit are shown like this. And the other way to align start from this 2 was shown as by an insertion of a 3 after the first 2. So it break this x round 2, 2 into 2, 3, 2. And the next round to match in x is this 3, it's length 1 round. In y Now it's this length 3 run. So L1 is 1, L is 3. So it must be the case where there is one deletion in between, which lengthen the run by combining this 3 and these 2 3s. So in this case, we can also get 2, 3, 2, 3, 3, 3. So in this part, we show an ambiguous local alignment give 2 different global alignment. And in this case, we would write 1 bit to indicate which global alignment it is. So after we've shown that X and Y hat can be almost aligned, we can characterize the typicalized nature's secret, which is h of E hat given X, Y hat by 2 terms. The first term is the global alignment. So when we are not able to tell which global alignment it is, we write 1 bit to indicate. The second term is h of E hat given X, Y hat and the alignment A. So with the help with A, we will be able to align X and Y hat. And once we align X, Y hat, the nature secret only lies in the locations of single deletions in length L run, which would be log L, and the location of a same single insertion in length L run, which is given by log L plus 1. And these 2 terms can be calculated. For details, we refer to the part 3.a in our paper. After we calculate the typicalized nature's secret, we shown the typicalized nature secret is close to nature secret. Here we refer Canary and Montanari's paper. We invoke a fact in there. So here, the first 2 tuple of variables E, X, Y, and E hat X and Y hat are related through E complement in the following way: that E, X, and Y is a deterministic function of E hat, X, Y hat, and E complement. And also, the right-hand side E hat, X, Y hat is a deterministic function of the left-hand side and the E complement. Similarly, the pair XY, XY hat are related through E complement and the alignment A in the way that XY hat can be determined from XY, E complement, and A. Also, XY can be determined from XY hat, E complement, and A. So the fact in the Canary and Montanari's work says that if these 2 pairs of variables satisfy this relation, the entropy of X given the entropy of E given XY minus the entropy of E hat given X and Y hat can be upper bounded by the entropy of the entropy of E complement and the entropy of E complement A. basically the variables on these two direction arrows. Here we give some examples showing how these two relations can go both directions. So the first one is more straightforward because E complement is defined by indicating the edit we eliminated. So so firstly we show the direction from the right hand side to go to the from the left hand side to go to the right hand side. So with E and E complement, we just eliminate the edit indicated in E complement. We eliminate in this way. So for insertions which are eliminated, we just remove them from E to get E hat. For deletions which are eliminated, we change this deletions delta into non-operations alpha to obtain E hat. So this is from E to E hat. And once we have once we have E hat, Y hat can be determined by processing E hat on X. So next we show the direction from the right hand side to the left hand side. So we go from left to right. When we see an delta underline in E complement, it meant that we eliminated a deletion here. So we change the corresponding alpha in E hat to delta to restore this deletion. And then we see an alpha underline which indicates we eliminated an insertion to get E hat. And now because eliminating an insertion, we removed it. So now we insert this alpha back to obtain E. And similarly, when we see this delta underline, we restore by change the alpha back to delta to get E. And once we have E, we have X. Y can be obtained from processing E on X. So this shows how the two directions can go from the help of E complement. The next relation is more complicated. So in this relation, the easier direction is from the right hand side to the left hand side, because X and Y hat can be almost aligned as we showed before, and with the help of A, they can be aligned, which means we know which rungs in Y match to which parent rungs in X. And once we know the alignment, we can also align E complement in this way. So now in the parent rung matches where the E complement are all non-operations, we know that we eliminated no edit in those rung or rungs. So in those correspond rungs, Y and Y hat should be the same because we didn't change anything. In those rungs where there are delta underline or alpha underlines in E complement, we eliminated those edit That's why we see in this example the run in y hat and x are the same, because we eliminated all the edits in this run. And to get y, we just apply this edit back to this run to get the corresponding run or runs in y. The direction from the left-hand side to the right-hand side is more complicated because in general, x and y are difficult to align. But we can show that by trying to align x, y, and e complement, we will figure out the wrong alignment when the result doesn't give y. So here is an example. So firstly, we look at the first run in x. It's 0, 0, 0, and we look at so the length of this run is 3. We look at 4 symbols in E complement. It's all non-operations. So we knew that we eliminated no edit in this x run. Hence, x and y, the actual edit satisfy the condition of the typicalized edit pattern. So we can try to align x and y based on the similar aligning algorithm as x and y hat. However, in some alignment, for example, in the first alignment, we align the first run of y to the first run of x through one deletion. And in this way, we can also align the E complement to them. And then later, we would know that in y, there's a 0 after this 1. So there must be an insertion of 0 here. And again, we align 2 non-operations in E complement, means there is no edit eliminated here. So up to now, there are 5 non-operations in E complement. The next one must be delta underline, alt underline, and delta. They indicate the edit eliminated to get the typicalized edit pattern. Actually, they also indicate the actual edit that had happened. So we would know that there was one deletion and one insertion 4 here, and one deletion here. And by applying this, we can get y to be 0, 0, 1, 0, 4, 1. But this result doesn't match with the real y, because this is 1, 0, 1, 4, 1. It's missing a 1 here. So we would know that this is not the possible alignment. So for the first run, we will go for the alignment where there's an insertion of 1, which break the run x, the 3 zeros, to 2 runs, the 2 zeros and a 1 0. And the remaining are just similarly. And when in the last part, there is again an ambiguous local alignment. But with the help of A, we would know which one is the correct alignment. So after successfully aligning X, E complement, and Y, we can eliminate those added indicated in E complement. And by eliminating this added, we will get Y hat. So this shows the direction from left-hand side to right-hand side. This is just a repeat of the proof sketch with the result. And this is the main theorem for the information theoretic lower bound for the random model. Next, I'm going to talk about the lower bound for the arbitrary model. In the arbitrary model, because we care about the worst case communication complexity, we define the X post-added set as the set of all sequences that may be obtained from X. So if the pre-added sequence is X, and there are this the log should be absolute, but it should be the size of the X post-added set. So given a pre-added source sequence X, then we need log of the size of its post-added set, such many bits to indicate which post-added sequence it is. Hence, to find a good lower bound, we need to find a pre-added sequence with large post-added set. Here we show some iterations for the only insertion process and only deletion process. For the only insertion process, the pre-added source sequence, which will give large post-added set, is a sequence with all the same symbols. So it's just a length n run of the same symbol. For this pre-added source sequence, we look at a subset of insertion patterns where the epsilon and insertions can happen in arbitrary positions, inserting arbitrary symbols other than alpha, which is the symbol in this sequence. Applying these added patterns to the pre-added source sequence, all the post-added source sequence are different, and the number is given by this. So the optimal rate for the only insertion process is the lower bound is entropy of epsilon over 1 plus epsilon times epsilon log A minus 1. The physical meaning of this is basically the positions of the insertions and the content of the insertions. For the only deletion process, the pre-added source sequence we find, which will have a large post-added set, is a sequence with all distinct symbols. In this case, too, we are just giving some iteration. In this case, the alphabet size is at least m, which is which is unbounded. But this would give intuition. So for this sequence, by deleting arbitrary delta n symbols in the sequence, all the post-added source sequence will be different, and the number is just n choose delta m. The lower bound for the optimal rate for the only deletion process is h delta, and the physical meaning of this is the positions of the deletions. However, when we mix insertions and deletions, the problem becomes more challenging. The first reason is that in the only deletion scenario, the alphabet size is at least n, where n is the block length. The second challenge is that the pre-added source sequence we constructed in the only deletion and only insertion cases are rather different. In the only insertion process, the sequence is all same symbol sequence. In the only deletion case, the pre-added source sequence is all different symbol sequence. So to find the lower bound for the arbitrary model, we construct a pre-added source sequence, which we call block-wise distinct pre-added source sequence. So in each block, the block length is A/2, where A is the alphabet size. In each block, all the symbols are different, and in the end of the block is a fixed symbol, in this case symbol 0, which act as separators to indicate the boundaries of each block. The corresponding subset of added patterns to get different post-added sequences are in the following way. So all the deletions occur before the insertions. The delta n deletions may delete any symbols in the sequence other than the separators. And the absolute insertions can insert arbitrarily any symbol from the other half of the alphabet. So this sequence X sub BD, this block-wise distinct sequence, is built using only half of the alphabet. And when we insert arbitrary location, but only symbols from the other half of the alphabet. We can show that the post-added source sequence by applying this subset of added patterns to this pre-added source sequences. Pre-added source sequence is all different, and the number is given by this term. And by Stirling's approximation, we derive our lower bound for the optimal rate. And furthermore, if we can use Taylor expansion to get this lower bound, where up to the first order of epsilon, delta, and log A. The lower order term is in order of epsilon squared, delta squared, and 1 over A squared. Now I'm going to talk about the attributability. The algorithm for the attributability is unified for both arbitrary model and random model. So the encoder do the following. The encoder reads the source sequences X and Y, apply dynamic programming. The dynamic programming output an added pattern tilde E. And the encoder uses an entropy encoder to encode the edit pattern tilde E to output the transmission T. The decoder receives T and apply the entropy decoder corresponding to the entropy encoder used by the encoder on T to obtain the edit pattern tilde E. And by processing the edit pattern tilde E on X, it reconstruct the new sequence Y prime. Dynamic programming is well known in literature to find the edit distance of two sequences. So the edit distance is the total number of the smallest total number of edits that needed to convert a sequence to the other sequence. And it can be shown as a fact in the section 4b that when there is when the edits are only insertions and deletions, not only the total number of edits are minimized by dynamic programming, but also both the number of insertions and the number of deletions are minimized. In the attributability for the random model, we firstly show that the number of deletions and insertions can be concentrated by chain of bond, because the number of deletions is sum of n IID Bernoulli, and the number of insertions is sum of n plus 1 IID geometric distribution, geometric random variables. Hence, with probability 1 minus the order of e to the power minus square root n, ki and kd can be upbounded, can be concentrated not far away from their expectations. And we can characterize the transmission rate contributed by this scenario. With probability smaller, exponentially small, kd and ki is from their expectation to n, and the transmission rate contributed in that case is linear in n. So it's negligible when n goes to infinity. The number of deletions is upbounded by n. However, the number of insertions is unbounded. Actually, the number of insertions is the negative binomial distribution. However, we can still concentrate the probability when ki is greater than n, and the transmission rate contributed in those scenarios, and the probability decays much faster than the growth in the transmission rate contributed. And as the block length n goes to infinity, the information rate contributed by those scenarios are also negligible. Hence, we can show the attributable rate for the random model. And we apply Taylor expansion to get a form similarly to compare with the lower bound. For the arbitrary model, the attributability is the proof of the attributability is similar to the random model. The difference is that the number of insertions and deletions are bounded in the arbitrary model. They are bounded by epsilon n and delta n respectively. The second difference is that we care about the worst-case communication complexity in the arbitrary model. And in the end, we show the achievable rate for the fourth arbitrary model is given by this. So here is a summary and a comparison of the results. I'm going to draw 3D figure of the inner bounds and outer bounds, and I will update this PowerPoint later. Thank you.